Okay. Hello, everyone. Welcome to the webinar series on Rate Splitting Multiple Access 2022, organized by IEEE ComSoc WTC Special Interest Group of RSMA. This is our second webinar this year, and it's our great honor today to have Professor Vincent Wong from University of British Columbia as our distinguished guest speaker. So please allow me to make a brief introduction of Professor Wong first. So Professor Wong is now a full professor in the Department of Electrical and Computer Engineering at the University of British Columbia, Vancouver, Canada. His research areas include protocol design optimization, resource management of communication networks with applications to the internet, wireless networks, smart grid, mobile edge computing, and Internet of Things. And currently, Professor Wong is the chair of the Executive Editorial Committee of the IEEE Transactions on Wireless Communications and area editor of the IEEE Transactions on Communications and the IEEE Open Journal of the Communications Society, and an associate editor of the IEEE Transactions on Mobile Computing. And before the talk, I would like to remind the rules of our webinar. So during the 15-minute talk, please keep yourself muted and you can type your question in the chat box. After the talk, we will have an around 10-minute Q&A session. So you can unmute yourself to raise your question, or I will choose 2 to 5 questions from the chat box. Okay, enjoy the talk. So let me stop sharing. Professor Wong, I think you can start sharing your screen now.
Okay, let me do it now. Okay, can you see my screen?
Yeah, perfect.
Okay, let's get started. So thank you very much for the invitation to give an online talk today. And I'm very happy to share with you some of the results we do in the area of rate splitting. So the title for the presentation today is Rate Splitting for Intelligent Reflecting Surface Aided Multi-User Virtual Reality or VR Streaming. So this is a joint work with my PhD student, Rui Kwang, and also my collaborator, Robert Schobert. So Rui, of course, is at UBC, and Robert is at the University of Erlangen in Germany. Okay. So in the area of 5G and beyond, and also the 6th generation wireless systems, there are many new use cases and also applications as well. One of them is in the area of virtual reality. And there are many new applications or important applications in this area. They are related to online learning, remote surgery as well. Of course, online games will be an important area. And also virtual reality will be part of digital twin as well. So there will be more and more applications in this particular domain. And in this talk, we are focusing on using virtual reality in an environment that there are a large number of users who are trying to actually share a particular real-time virtual reality streaming application. And that is the use case we consider in our work today. But some of the results that we consider in this work are also applicable to other applications as well. In the area of virtual reality streaming, if we look at different types of the head-mounted devices or headsets, and typically some of them, the data rate are on the order of about 30 megabits per second. And we expect that the rate will actually be increased further depending on whether there are emerging applications in this domain as well. So what we want to emphasize in this part is the fact that there may be more and more people which have these kind of headsets. The size may decrease and the price will reduce as well. But we also look at the scenario that what happens if there are a large number of users within a given area and who are using these particular devices. So this is a little bit different from in the 5G or 6G domain. People look at, say, massive IoT devices within a large area, tons of IoT devices. We look at the case that within a given area, what happened? We have a large number of these virtual reality streaming devices, and what can we do to actually improve their performance? There are many interesting topics in the area of virtual reality streaming. And a lot of people, colleagues in ECE and also in computer science are working in this area as well. One of the issues people have studied is, or one of the potential limitation of using virtual reality streaming is that a small percentage of users may have a illness, which is the motion sickness. And this motion sickness is not the same as the typical motion sickness that you get some sickness when you're in a car or if you're in a ship. But instead, if you're putting on your hand-mounted devices, and somehow if the data tiles or the video tiles are not received within a particular delay, then the user himself will actually have some kind of uncomfortable symptoms, and that is. In this area, people also call that as the motion to photon delay. So what people want to make sure is that those video frames and video tiles have to be delivered or received by the headset device within a particular time delay. So this is we look at real time instead of non-real time applications in our work. This slide is related to brief introduction about 360-degree video streaming. And in our work, we look at the case that if many users in a given area, they look at the same picture or the same frame. In 360-degree video streaming, when you put on your headset, some users may look at a particular area, and some users may look at a different area. In that case, if you have a large number of users, some of them will actually have what we call the shared interest. So they will look at the same group of video tiles. So in this example here, suppose we have 3 users, user 1, user 2, and also user 3. And user 1, the video tiles that user 1 is looking at, which we call the field of view in this example, they correspond to video tiles 14, 15, 20, and 21. User 2, as an example, the user is interested in video tiles 9, 10, 15, and 16, and so on and so forth. So we notice that at any given time, if we have a number of users who look at the same view, some of them will have an overlap. And what we want to do is we want to look at how we can actually use ray splitting to actually exploit the shared interest of the video virtual reality users that have they share a field of views. Another example that we can give is if you look at a particular soccer match as an example, we may be say 2 teams, team A and also team B. Some of the supporters of one particular team may focus on their own favorite teams, and some others will only focus on the other teams, and some others, of course, will just focus on where the soccer ball actually is. So based on that, we want to look at the case of how we can support real-time video streaming, but at the same time, we can make use of the fact that some of the data video tiles requested by the users, they are correlated, or we will simply say there's a shared interest of those users. For some of the existing works in the area of multi-user wireless systems that support virtual reality streaming, we can broadly divide it into 3 particular classes or 3 particular groups. The first one is by using spatial division multiplexing. So in this case, all the users, they would treat the corresponding data stream to be independent. So we do not consider any correlation or any shared interest between them. So if we, in this case, the signals from other users will simply be treated as interference. So that is the typical way of using spatial division multiplexing if you have a large number of transmitter antennas to support a large number of users. The second one is using OFDM. In this case, we can, as an example, locate particular subcarriers or OFDM symbols to different users. So in this case, we can support a large number of users, but then we do not consider the correlation of the shared interest between a number of users. The third group is actually by using multicasting. So in this particular case, in general, the way we do that is we first divide the group total number of users into different groups. And for the users in the same group, we simply send or transmit the same video tiles to those users. So in this case, those users will simply receive the same information if they're in the same group by using multicasting. This is a good scheme and the results have shown good performance. But then in terms of complexity, at a certain time period, the the VL server may have to decide to optimize for a particular user, whether the user should be in, say, group 1 or group 2 or group 3. So it needs to decide the grouping, and that can actually be computationally intensive in this particular case. And the energy, the spectral efficiency may not always be fully utilized or improved. So in this work, what we want to do is we want to use rate splitting to exploit the corresponding shared interests between different users. So given the fact that some of you have already attended the previous rate splitting talks last year and also the one last week, so I will not give a detailed introduction about rate splitting, but we'll simply say that we make use of the common message and also the private message of rate splitting. So the idea this time is if we use the same example one more time, we have 3 users, user 1, user 2, and also user 3. They request different tiles and they have different interests. So in this case, the video tiles 10, 15, and also 16 in this example are requested by more than one user. So one simple way we can consider that is we can put those video tiles that are common to some of the users into the common message of by using rate splitting. And some other video tiles which are which we call unique to those users, we simply put that as individual private message of those users. So in this example, if I continue to the same example again, so by looking at this figure, you will notice that first of all, the users, user 1, user 2, and user 3 will inform the base station at the next time slot what are the video tiles that I'm interested in. So when the base station has received the information, the base station will decide what are the information that should be put in the common message, and also decide what are the corresponding information or the video tiles that we want to put in the private message as well. And then it will create the common message and the private message and send to the users. And by using rate splitting, the user will have to decode the common message first before it can decode its own private message. So in this toy example, we give a very simple explanation to explain that. And for now, we assume that, say, video tile 15 as an example, the one showing here, which is requested by user 1 and user 2. And this message or this video tile, the complete video tile, is put in the common message. But later on in our work, we will explain that it is possible that video tile 15 as an example, it is possible that part of the information in video tile 15 is encoded in the common message, and part of it is encoded in the private message as well. So that is, we consider a more general case in our work, but we simply use this toy example here to give an illustration about how we can make use of rate splitting to exploit the shared common interest between different users. Okay, so if we want to use rate splitting to support real-time virtual reality streaming, So there are a number of questions that we want to address. The first one is the one that we mentioned previously, is among all the video tiles requests that the base station has received, which video tiles, or what are the set of video tiles that should be put in the comment message? That is, should be a relatively simple question. The second one is within the comment message itself, it will be sent by the base station to all the users at a particular rate, and we want to figure it out what is the proportion of the rate that is dedicated for a particular video tile. So back to our example, if the comment message has to send, say, video tile 15, 16, and 17. So we want to figure it out what is the proportional rate that we want to dedicate it for, say, video tile 15 as an example. So similarly, we also need to send some of the remaining video tiles in a private message. And we also need to decide what are the proportions of the transmit power that should be allocated to the rate and transmission power that we want to allocate to the comment message and a private message as well. So in this case, among these three questions, the first one is related to what are the corresponding tiles that should be in the comment message or in the private message. The second one is related to the proportion of the rate that we want to put in the comment message and the private message. The third question that we want to address is the base station has multiple transmit antennas. So we want to, the third one is essentially a beamforming problem that we want to figure it out the corresponding beamforming vector that we want to use. So these three are related to the rate splitting aspect. And then the next one, the next part we want to do study is the corresponding potential performance bottleneck of rate splitting. And for many of us who have studied the basics about rate splitting multiple access, some of the basic principle is that in rate splitting multiple access, the comment message needs to be decoded by all the users before the user can actually decode the private message. In this case, the achievable data rate of the comment message is limited by the user, which has the lowest signal to noise plus interference ratio, the lowest SINR in this case. So if you support a large number of users by using rate splitting, in that case, if one particular user has a relatively low SINR, then the corresponding rate will actually be relatively low. So in this case, we will not be able to get the benefits of using rate splitting in this particular aspect. So the second part we want to do is we want to further improve the corresponding common rate. And the technique that we consider is actually by using intelligent reflecting surfaces so that we can introduce another line of sight channel so that it can improve the rate further. So some of the basics or fundamentals about IRS intelligent reflecting surfaces. So IRS essentially is simply a planar surface with a large number of reflecting elements. And each reflecting element can be allows the controller to actually decide the corresponding phase shift to the incident signal. So in this case, IRS can create another channel for the receiver to user to receive the signal, and we can reduce or mitigate the corresponding interference if we carefully control the corresponding phase shift. By using IRS combining with rate splitting, the benefit that we can obtain is that the minimum SINR can simply be improved. So in this case, this leads to the fact that we can further improve the corresponding common rate in rate splitting system. So that is why we consider this particular aspect. So what I'm going to do now is we are going to first describe some of what we consider in the system model, and then we're going to describe the corresponding solution approach. So the system model is as follows. We consider an indoor environment with a certain number of users. So in this figure showing here, I only show one particular user N as an example, but we consider a group of users within an indoor environment where one base station on top and in one of the walls there is an intelligent reflecting surface, IRS. And we make two assumptions. The first one is that the user has limited mobility. We consider that the user may be playing some online game and the user will only move within a particular area. So in this example here, we assume that user N can only move within this particular area denoted by this yellow color here. And at the same time, we also make an assumption that the base station can actually obtain the perfect CSI information from all the end users in this particular case. Later on, when I present the results, we will show the results of what happened if we have imperfect CSI. And in the very end, we can also show you some of the future research directions to consider the case for imperfect CSI as well. But for now, we assume that the base station can obtain all the has the acquired perfect CSI information. So that is related to the system model. It's indoor environment, number of users. Each user has a virtual reality hand-mounted device to receive the corresponding downstream video frame or video tiles. And the second part is related to the video tile request. So we consider that each particular video frame is divided into a finite number of video tiles. And not all the users will try to obtain all the video tiles. Each user may only look at one particular direction and only want to obtain a subset of those video tiles. So we simply use the notation I sub n to denote that for user n, what are the video tiles that this particular user wants to obtain. And in this case here, in this figure, what it shows is that user n at the beginning of a time slot, it will inform the user, I want to obtain, say, video tiles 8, 12, 15, 20 as an example. So the base station will obtain all the information from all the users in this case. Nowadays in the research community, especially in computer science, there are also many papers which describe how to either decide what are the video tiles or how to predict the video tiles as well. In this presentation, we make a simple assumption that the users, they know at the beginning of the time slot, what are the video frames that this user wants, and simply send the information to the base station. And this work can also be extended by considering video tile prediction as well. And the next part is related to the bit rate. So we consider that for a particular video frame, it can be encoded into m different bit rates. So the user, the virtual reality server, based on the corresponding CSI information obtained by all the users, it can decide for this particular user, the bit rate should be used for playback in the application layer, should be in one of those rate from v sub 1 all the way up to v sub n. So if uppercase M is equal to, say, 3 as an example, we can consider that the bit rate can be, say, low quality, medium quality, or high quality as a simple example. So this is actually the rate for the video tile for user N. This is a decision variable made by the corresponding virtual reality server. So that is not something that the user say, I want this particular rate, but this is decided by the server based on the CSI information. And that is also one of the optimization variables that we want to determine as well. And since different users will request different frames, and different frames will be sent, video tiles will be sent by different rate, in the area of virtual reality streaming and also in multimedia as well, there are different metrics to capture the performance degradations related to the fact that from one video tile to another video tile, the bit rate may actually be not the same, or within a group of video tiles, the rate may not be the same as well. So in this work, we use one metric, and that is called the intra-frame quality switch loss. And it's given by this equation here. And this one is nothing but simply, you can consider that as the corresponding variance of the bit rate obtained by user N. So the second term, which is the one showing here, is essentially the average or the mean of the rate that the user n will obtain among all the video tiles it requests. And v sub n minus the mean, and then you take the square. This one, you can consider that as the variance. So based on that, the utility of a user in each time slot, we can model that as this function here. The first term corresponds to the aggregate bit rate, the aggregate rate of the user n for all the video tiles that the user obtained. And the second term is the corresponding performance degradation, or the QoS degradation, due to intra-frame quality switch loss. So we consider the rate and also the corresponding switch loss in this case. And of course, we need to have a coefficient or kappa as a scaling factor to make sure that we don't have one term which is much greater than the other term. So now we move on to describe the corresponding information, some other information that needs to be decided by the server, especially what we want to decide related to the base station by the base station, and that is the corresponding beamforming factor. Okay, we have the common message, and also we have the private messages as well. So in our notation, we use b sub 0 to denote the beamforming factor of the common message, and for the private message, for user n, we use the notation b sub n to denote the beamforming vector for user n. So in this case, when a user n receives the signal coming from the base station, it is represented in this format here. So notice that the user n will receive the message directly from the base station. The user will also receive the message, which is signal sent from the base station, reflected by the IRS intelligent reflection surface and back to the base station. So in this case, the first term corresponds to the signal of the common message. Second term corresponds to the signals of the private messages. Last term corresponds to the signal due to noise. And we also have the maximum transmit power constraint showing here. So that is, this part is related to the beamforming vector design. So the next two slides are essentially, or I would say, common equations people use when they study rate-splitting multiple access. This one is related to the SINR of the common message at user n in a particular time slot. So this is the first term is due to the direct line of sight from the base station to the user. The second term is due to the reflected signals coming from the IRS, and we have the first part is the interference. You can consider that as an interference due to the private messages and the variance showing here. Constraint 3, which is the one showing here, corresponds to the rate of the common message. So we use the superscript C to denote the common rate of the common message. And that is essentially the minimum of the rate of common rate of user 1, user 2, all the way up to user n. So again, because of this minimum here, this rate, the one on the left-hand side, is limited by the user which has the smallest SINR. And again, I will emphasize that by using IRS, we can further improve the user which has the lowest SINR, and we want to increase the value further so that we can increase the common rate. And that's why we use the IRS in this case. And the next two slides are related to the proportion of the rate. So we use the notation C sub I to denote within the common rate what is the proportion of the data or the rate that is dedicated for the transmission of video tile I in this case. So C sub I, you can consider that as a percentage of the percentage of proportion that is between 0 and 1. And typically it should be set to 1, but in optimization problem, we can simply set it to less than or equal to 1, because at optimality, it will simply be equal to 1. So in this case, by determining or optimizing C sub I, the base station can decide for which video tiles should be included in the common message. If for video tile I, as an example, if C sub I is equal to 0, it means that video tile I will not be part of the common message in this particular case. If it is equal to say 0.2, it means that 20% of the time within that common message, it is used to send video tile I in this example. And the SI now of the private message is actually showing here. And this is the numerator showing here corresponds to the private message received related to user N. And in the denominator here, the first term corresponds to the private messages of other users, excluding user N. And we can then determine the corresponding achievable rate of the private message for user N given by this expression here. And similarly, the private message will be used to carry multiple video tiles. So we need to use a notation P sub Ni to denote for user N, what is the proportion of that private message that is used to transmit video tile I in this case. So the sum of this proportion is equal to 1. We set it to less than or equal to 1. And the last bullet showing here is the fact that for video tile I as an example, if C sub I is positive, it means that in the common message, I will carry video tile I some information. And at the same time, if in a private message of user N, PNI is also positive as well. So it means that within the video tile I, part of it will be carried in the common message, and part of it will be carried in the private message as well. So that is what we mean by this particular expression here. And the second last constraint that we want to introduce is related to the fact that the server will use a particular rate, and we want to make sure that we can actually receive the corresponding number of bits that allows the user later on to actually have sufficient data to play back. So this one itself, we call that the for per user perspective, for particular video tile I, what is the corresponding quality of service requirement? So this J-mean is not a constant, but instead it depends on the video tile selected by the bit rate selected by the server to support this particular user. And in our optimization, the last constraint is the C9, and that is the phase shift constraint. So for if the IRS has say L reflecting elements, we want to make sure that among these L reflecting elements for each one, what is the corresponding phase shift? So in this optimization problem that we want to study, we want to maximize the aggregate utility. And the utility is a function of the bit rate and the corresponding intra-frame quality switch loss. And we have a set of optimization variables. And these optimization variables include the phase shift, which is our constraint C9, the beamforming vectors, which are our B showing here, beamforming vector of the common message, beamforming vector of the private message, the rate splitting parameters, that is within a particular message, what is the proportion of the video tiles that I want to carry in the common message and in the private message as well. The last one is the bit rate selection of the video tiles. So for each particular tile, you want to send as say a high rate, medium rate, or low rate. So that is related to the bit rate selection. So within this, you will notice that the bit rate selection, these are the integer variables, and the rest, they are continuous variables. So in this case, this problem that we formulate here is a mixed integer non-convex optimization problem. Of course, there are many heuristics available that allow us to solve this particular problem. One of them is by using alternating optimization. In this case, it will allow us to obtain a suboptimal solution. But this approach can be computationally intensive, especially when we want to support real-time virtual reality streaming that may have a timing constraint that you will want to decide the solution within a particular time frame. So what we want to look at is we want to look at an alternative approach that allow us to obtain a solution in an efficient manner or within a certain delay bound. So the approach that we look at is actually by using machine learning approach combined with what we call the human knowledge. So the approach that we propose, we give a name, we call it deep deterministic policy gradient with imitation learning, deep grade algorithm. So this approach is a combination of deep reinforcement learning and at the same time, we combine with the human knowledge of the wireless system. So in particular, we make use of the hidden convexity of the formulated problem that I showed in the previous slide by using imitation learning. So what we are going to describe is try to describe these components here. So this particular figure shows for the proposed deep grade algorithm, what are some of the components that we have. So if we look at the left-hand side, we have the deep reinforcement learning. And deep reinforcement learning, essentially, we have at a given time slot or decision epoch, we are in a given state, so the agent has to choose an action. So once the action is chosen, the agent will receive a reward, which depends on the current state and the action chosen as well, and then it will move to a different state. What we do in our work is that we make use of deep reinforcement learning. We combine with DDPG, active critic method as well. In order to avoid overestimation, we also use the n-step bootstrapping or multi-step bootstrapping. And within the active network and also within the critic network, we also come up with our own design for the deep neural network, which we give a name called the RoughNet. And the RoughNet actually make use of some of the information from the right-hand side, and that is what we mean by the hidden convexity. So what we did in this part is that we also use the conventional AO approach to solve a subset of those problems by decompose the problems into multiple subproblems, and then use convention techniques, including semi-definite relaxation, fractional programming to obtain the suboptimal solution. But the suboptimal solution, as the name implies, may not be optimal. And we fit this information by using a technique called imitation learning to the RoughNet to actually guide the corresponding agent to learn the good solutions. So the learning agent may use some of the solutions based on the one provided by imitation learning. At the same time, the learning agent may also be, by using exploration, may actually be able to discover or learn some other solutions, which has a higher utility than the one obtained by the traditional approach. So in this case, essentially what we can do is we can actually expand the corresponding search space and search for better solutions for this particular problem here. And that is what we mean by combining DRL with imitation learning technique. So in the next 5 to 10 minutes, what I'm going to do is to give a brief overview and also describe some of the results as well. So in our work, what we consider is we first consider that within each time slot, we simply divide it into multiple decision epochs, tau max of them in total. And we have the state vector, which is given here. And the state vector includes 3 groups of information. The first one is the CSI information. As we mentioned before, we assume perfect CSI. The second group of state information corresponds to the decision variables. That is something that we decide in the previous decision epoch. And then the last group corresponds to the video tau request that the user sent to the corresponding base station. And based on the state information, the learning agent will be able to decide the action. And the action, of course, corresponds to the, what we want to optimize. And they include the beamforming vector, the corresponding phase shapes, the corresponding RS rate splitting parameters, the proportions of the video tags we want to put in the comment message, the corresponding private message. And finally, what we want to determine is the bit rate as well. So those are the actions that we want to determine. And we did a number of tricks or techniques to actually obtain good performance. One of the tricks that we do is due to the fact that in the objective function that we have, because the bit rates that we want to select, they are discrete integer variables. In machine learning community, some of the papers, they call that sparsity. And in this case, one way to actually deal with sparsity, and in our work, we also want to make sure that our reward function can capture the state and the action. So we use a similar monotonic transformation, and we define the reward function not to be the same as the utility function, but actually proportional to the utility as well by using this expression here. So that the reward function is a function of the current state and the action chosen as well. And we are going to show later that if we don't use this technique, what kind of results that we will get by showing you some ablation experiment. And we have the active network and the critic network. For now, in our presentation here, I just give a brief overview and then describe the RAFnet details later. So the active network, what it needs to do is it wants to learn a policy, which we give a name, pi sub phi act, which include the parameterized learnable parameters. So the phi act is something that the parameters we want to learn. And after that, the policy corresponds to the fact that given a corresponding state, we can then determine the corresponding action. And a critic network, on the other hand, is to approximate the state value function. And typically, people what they call as the Q function, which is the one showing here in this equation. So this part we make use of when we describe here is similar to DDPG, but then I will describe later that using RAFnet, we also include the corresponding constraints in the actor and critic network as well. And now we also mentioned that we want to use imitation learning to improve the performance. So how does it work for imitation learning? So first of all, in the formulated problem, we noticed that based on the SINR expression, there is a hidden complexity. So we can indeed use alternating optimization to obtain the suboptimal solution. So the way we do it is as follows. In AO algorithm, it's an iteration algorithm. So for each iteration, we simply map each iteration corresponds to a decision epoch. So in MDP, one decision epoch corresponds to one iteration in this AO algorithm here. So given the CSI and the video tile request, we solve the AO algorithm. In each iteration, we obtain one solution. When the algorithm converge, then we have the corresponding solution here. So if we look at the figure on the right-hand side, you can look at the case that you start with an initial state or the solution. So eventually, when the algorithm converge, you are actually within a corresponding state and an action, which can provide the highest reward. So that is what the iterative process is all about here. And we solve this AO problem here in the different time instance or different time source. And we also call that as the different trajectories. And we store each trajectory. So each one here corresponds to different iterations as a demonstration replay in our neural network. So if we have D trajectories, so we simply store all the information into what we call the demonstration replay in this case. So after that, we determine what we call the imitation loss. So on one hand, we use the AO algorithm to actually have different trajectories. And at the same time, we can use deep reinforcement learning to actually solve the same problem and determine the action or the solutions as well. And we want to look at the difference. And the difference, we simply give a name, we call that the imitation loss. And the technique we want to use is that we do some filtering. The term which is used in machine learning community as well. We only consider those actions from the AO algorithms or the solutions of the AO algorithms, which are better than the one that we obtain by deep reinforcement learning. We consider them. If we use MDP or deep reinforcement learning, which we give a better solution than the AO, then we will not consider that. So the imitation loss is the one that we define in this expression here. And after that, in our modified actor critic method, in this case, by using the modified gradient update, we consider two factors. The first one is the gradient of the corresponding DDPG, which includes the constraint, which we will describe the constraint later. And the second one is the gradient, which we consider the imitation learning. So our overall framework includes not the conventional way, but we have the experience replay, as well as the demonstration replay, and the information from the demonstration replay is coming from the AO algorithm. And our active and critic network as well, both the active and critic networks, we also include the RoughNet, which we are going to describe later. And apart from that, in machine learning community, people notice that in order to avoid the overestimation issue, instead of using one critic network, people advocate or suggest the use of multiple critic networks as well. And we also consider that in our work. So the last part before I present the results, what I'm going to do is to describe what exactly is the RoughNet that we have here. And the RoughNet itself, why we want to decide this one, we want to capture the corresponding correlation or the positional information between different elements. And the second part we want to include is the fact that in our optimization problem, we have a number of constraints which are related to the bit rate and also related to the corresponding beamforming as well. And we make use of a technique which is called the differentiable convex optimization layer, which is given by the last reference in the footnote showing in this slide here, to actually allow us to obtain the solution. So in a RoughNet, which this module is included in the active network. So we first divide the state information into two groups. One is with the CSI information and also the corresponding rate related to the C sub I and P sub NI, which are the information, the proportion of the tiles for the common rate and also the private message as well. So it needs to go through the CNN, the multiple perception module, the DCO layer. And at the output of these two layers, we obtain the beamforming vectors, the phase shift variables. And this is one part. And the second part is what we also obtain the corresponding rate splitting parameters and the bit rate selection as well. So the last two layers is essentially allow us to more or less in a high level setting, solve two optimization problems and obtain the corresponding solutions as well. And by using these CNN and MLP, we can extract the corresponding spatial correlation or positional information related to different variables to obtain the results. So given the time I have, I may be over time by a few minutes. So I will do it a little bit faster. So we consider that we have an indoor setting with a finite number of users. The base station is located at the top of the ceiling with an IRS, which is located in one part of the wall. And we have different users, and each user has limited mobility within its own designated area, which are shown in this yellow color here. So that is the setting we consider. We consider all the users, they have line of sight because we want to look at what is the best performance that we can obtain by using rate splitting and intelligent reflecting surface. For the video tile request, we'll use the corresponding real-world video streaming data set coming from the reference R1. And what we want to show in this figure here is actually taken from R1 is that the x-axis corresponds to 7,000 or 10,000 frames, and the y-axis corresponds to 24 tiles. So each video frame is partitioned into 24 tiles. And these different colors shows that for a particular video tile, how many users are actually requesting that. So in this example here, those tiles which are in yellow color are the tiles that are requested by a large number of users. And the tiles which are in, say, dark blue colors, those are the tiles which are only requested by very few tile users. So these two figures are used to show that indeed at any given time, some users may actually request a particular set of tiles. And so those are what we want to mention before is that those are the shared interests of different users. And what I'm going to show is that we compare our proposed scheme with AO algorithm, conventional supervised learning. That is, we use the results from AO and then we learn or train a neural network. And then we compare with two other algorithms. One is the one by Lina, our host, and the other one is by Wu and Zhang, two papers which are published roughly 2 years ago. So the first one is used to show that by using rate splitting, we can indeed obtain a performance gain that is compared with the one which is by using just multi-user system that doesn't consider rate splitting, which is the one in a green curve here. This one shows that by using rate splitting, indeed, we can obtain a better performance. So that is what we want to show in this case here by increasing the number of reflecting elements. And when we look at this figure further, if we focus on, say, L is equal to 0, this is the case that we do not consider IRS. That is, some of the users will have the very small common rate. So in this case, compared with L equal to 0, we don't use IRS, compared to the case that we use IRS and L is equal to 100. Say we have 100 reflecting elements. In this case, it shows that the aggregate sum rate can indeed be increased almost by 100% or 90% if we use IRS here. So this one shows that by using IRS, indeed, it can obtain much better performance than not using IRS in this particular setting. And given the time I also just briefly selectively select a number of figures that I want to show. And this one, we want to show briefly what happened if the number of transmit antennas is equal to 6, but the number of users is actually equal to 8. So this is one way to show the overloaded scenario. And this one shows that we still have a performance gain. And this one most likely is due to the fact that because some users, they have the shared interest. So the rate of the common message is actually relatively high. So a number of users, they request the same video tiles. So in this case, the aggregate sum rate is still increasing in this particular aspect. So notice that in our case, in our problem formulation, because we have the minimum bit rate constraint. So eventually, if we increase the number of users further, it will not saturate. But in that case, the problem will become infeasible because we require that each user needs to have a particular minimum rate. So in that case, when N is actually getting larger and larger, eventually the problem will become infeasible. I'm going to skip one of the slides because we don't have much time, but instead I'm going to show the result of the ablation test. And this is the typical results people use in machine learning to show what are the effects of different modules or different components in the network. So we mentioned earlier that in our proposed scheme, we include a number of modules, active creating networks, multi-step bootstrapping as well. We make use of the imitation learning. So what happens if we actually remove one of the module and we want to look at what are the corresponding results that we obtain? So the first one, we notice that this is the top one here, which is the one in blue curve, is our original deep braille algorithm that we proposed. So we notice that if we do not consider imitation learning, there is a significant reduction of the system sum rate, which is the one showing here. So this one shows that imitation learning is indeed important. The second one is the reward approximation. We do not use the actual utility function we described earlier, but instead we use a mapping to decide our own reward function. And this one also shows that by using our own reward function, which can avoid sparsity, it also can show good performance. The last one is the Q-step return in machine learning community, or if you refer to a book by Richard Sutton, that is called the N-step return or the N-step bootstrapping. Because we have already used N, so we just call that Q-step return. So this one also shows that by using Q-step return, if we do not use that, then also there's a performance degradation as well. So the last slide that I'm going to show is what happens if we do not have perfect CSI. And this one shows that we assume that in our simulation, we use the conventional statistical channel estimation model. So we have the CSI or the channel gain plus another term, which is the delta H or delta G, and the delta is actually proportional to mu. So this one shows that when mu increase, say, from 10 to the minus 4 to say 0.01, the proposed deep braille algorithm can still retain the system sum rate, which is 85%, compared to the perfect CSI case here. So the very, very last one that I want to show is the runtime comparison. We mentioned that in virtual reality streaming application, there's a constraint. So this one shows that compared to all the other schemes, because other schemes, they require the use of AO to solve the problem. So AO algorithm takes a lot of time. So that's why many of these schemes require a large number of iterations to solve. Our scheme as well has a much lower runtime than some of the other schemes. Of course, it cannot compare with supervised learning, because for supervised learning, once you have trained the model, you already have the neural network parameters. You do not need to solve any problem again. But during our execution, we still need to pass the system state into the RAFnet, which also includes two differentiable convex optimization sublayers, DCO layers. And we still need to solve a convex optimization problem. And that's why it still needs some time to solve the problem as well. And in our future work, we are going to look at techniques which can reduce this time further. So to conclude, we propose a technique by combining rate splitting and RS, and by using a machine learning approach, deep reinforcement learning approach, we show that how we can obtain good performance in terms of the system sum rate. And in particular, we can improve this common rate much further. Some of the broader impact of our work is that this work can also be used to study problems where the information is actually correlated. And we can also use to solve problems which has constraints and that has hidden complexity. Our work is actually, there are many directions for further extension. One is the fact that we did not actually implicitly consider imperfect CSI in our model. So it is possible that you can, in imitation learning aspect, you can solve a problem which already consider imperfect CSI and use that as part of the information or knowledge in our work as well. And we can also combine with video tile predictions in our work. The long version of this talk is actually available in a submitted paper, which is available in archive. So based on that, that's conclude my presentation today. Thank you very much.
Thank you, Professor Wong, for the super interesting talk. And this is indeed a very new area for rate splitting. Okay, so we received two questions in the chat box from Sunda. Sunda, do you want to raise your question yourself? You can unmute yourself.
Sure. Thank you, Professor Wong. It was a lovely talk. The first question I had was in this example, in this slide, where you showed different tiles would be requested by different users. So here the tiles would be decoded out of order. And how does this affect latency in applications where the decoding order matters? If you're thinking about audio as well, in your football example, if it's linked to like commentary and things like that, certain things that appear later may be decoded earlier and so on.
It's a good question, Sunda or Sunda. My understanding is that out of order occurs when you transmit packets or data in a wire network, which has to go through multiple hops or multiple packet switches or routers. But in this case, in this work here, we only consider one hop transmission from the base station to the user device directly. So it's not clear to me how can the tiles be received out of order.
Okay, yeah, I think.
But what you are saying is correct. If somehow we need to go through multiple hops, then that will be an out of order packet reception issue. And in that case, well, I didn't consider that. And my short answer is that we assume that in the application layer, there's a buffer which actually store all the data bytes or data bits first, and then do the we only pass the order bits or bytes to the upper layer.
The other question was, you mentioned in your optimization framework, you had like a fraction of a tile that could be included in the common message, or this one. I mean, based on this example, it's like a tile is either fully a part of a common message or fully part of a private message. So could you clarify this?
I didn't. It's a good point. I use this figure here to actually show a simple example to get the big picture. But the other part I want to mention is that suppose you consider tile 15 as an example. So it is possible that, say, the first part of tile 15 is included in the common message, and then the remaining part of the tile 15 is encoded in the private message as well.
Okay.
That is what we want to actually describe, because at the end of the day, what we want to guarantee is that the user can indeed receive all the requested tiles within a certain time frame at a particular certain bit rate. So as long as we can actually make sure that all those requested tiles are received correctly, in the application layer, it doesn't really matter whether those bits are actually coming from the common message or from the private message. So that's why we allow a particular tile to be partially encoded or placed in the common message and partially put in the private message as well. And back to your question, I can also mention that if that part is actually not possible, we can also have another constraint to guarantee that a particular tile can only be put either in the common message or in the private message.
Thank you, Professor Wong, for the answer. Any other questions? If you have any question, please feel free to unmute yourself and ask Professor Wong directly. Okay, I actually have two questions, Professor Wang. So first of all is about your baseline on RS norm, which is also my work, because
I expect this question.
Yeah, because I'm not quite clear how you work as a baseline, because currently these video tiles might required by different groups of users.
Can you be a little bit specific about your question? I expect your question. Yeah.
Sorry, I mean that because in RS norm in my paper, I consider there is one string, for example, one string tile that is intended for all users. But in this specific application, if I understand clearly, is that different video tiles might be required by different groups of users. So
if I remember correctly, how Rui implement did this work is that correct me if I'm wrong, is that all the tiles in this part here, all the tiles are actually encoded in the common message, and in comparison, we make an assumption that the rate that is C sub I is the same for all the tiles. That is, we actually did not optimize C sub I when we compare with RS norm, but we set C sub I to be the same for all the tiles. That is our understanding of a paper. That is also, of course, there's a chance that our understanding may not be correct. That is the way we actually C sub I. That is, we put them in the common message. In our work, we actually optimize C sub I. That is our. Let me try to.
I saw the part that you mentioned to optimize it. So do you mean that for all video tiles that you considered for all users?
In the common message.
Okay.
In our work, in our proposed scheme, for each video tile in the common message, we decide the proportion. But when we compare with RS norm, you can correct me, we actually make the assumption that C sub I is the same. That is, suppose video tiles 1, 2, and 3, they are placed in the common message. We assume that C sub I is equal to 1/3. For C sub 1 is equal to C sub 2 is equal to C sub 3 is equal to 1/3. When we consider RS norm.
Okay.
That's our understanding about the RS norm.
Well, actually, in RS norm, we consider that there is one common string, but in this common string, we have, for example, like one video tile that is already initially required by all users. So there's only C0 for this string, because for this message, because it's already intended for all users. So there's no split of common message for this multicast string or a multicast message. Yeah.
If I explain it in a different way, the way we implement RS norm is that for all the tiles which are requested by the users, we actually put them all in the common stream, and some of the tiles we actually repeat that again in the private stream. That is first of all, so that we can actually guarantee the rate of each user. So the multicast is indeed because we're IMAX video tiles, not all the users request all the tiles. So we only consider, that is, if I go back to at the very beginning, that is in the last bullet here, these are all the tiles requested by all the users at a particular time. So when we compare with RS norm, we actually put all those tiles into the common message, and then we allocate the same rate. And for the private message, we transmit some of them again to the users. We will try to make it to be fair, but that is my understanding, or our understanding about the work. If we have some misunderstanding, we are happy to make changes.
I fully understand what you mean, because you put all of them in this common string. So that might be the reason that the performance of norm decreases, because all of them are in the common, and it will be limited by the worst case user.
We also use IRF to improve the minimum rate.
So I understand it. Okay, so for another question is related to another baseline you mentioned about this supervised learning. So my question is that when you consider supervised learning, did you consider this imitation loss as well or not? Because it seems to me that imitation loss is very critical to the performance of this of the proposed algorithm.
The way we implement the supervised learning is that we first solve a large number of AO problems, and we use that as the training labels. And then we use that to actually train a neural network. And that one is what we call the supervised learning. We did not consider the imitation loss. And you also notice that compared with the supervised learning, there's a gap with the AO here. And we in this particular set of results, we use 2,000, if I remember correctly, we use 2,000 training samples for the supervised learning. We expect that if we increase the number of training samples, this gap may decrease. But we also notice that it is actually very, very time consuming to obtain the results by using AO. So back to your question is, we did not consider imitation learning. We only consider the corresponding mean square error when we consider when we say supervised learning in our case, because we simply, once we obtain the results, we put that to train a DNN to do the job.
Oh, I see. But it seems to me that in the algorithm that you proposed, that you also consider to use AO results to calculate this imitation loss, right? So because you mentioned the sample you generated for the deep learning, for the supervised learning is 2,000, which is quite small. But so for the one that you considered in this, to calculate the imitation loss, do you how many samples do you consider there?
Well, this one we also use 2,000. So that's why we want to say, we want to make sure that the comparison is fair. So when I say 2,000, we actually solve 2,000 of those AO problems, and we use them for our algorithm as well. We use it for comparison of AO and also with the supervised learning, so that everybody actually has 2,000 samples.
I see.
So that's why we don't try to say we use 20,000 and the others one. We don't do that.
Yeah, this is actually the pretty much appealing part for using the deep reinforcement learning method, because it might require less training data from this AO algorithm to get a better performance. So this is what I understand. Yeah, very interesting.
Yes.
Yeah. Okay, so if there's no question, I would like to end the webinar today. Let's thank Professor Wong again for the very, very insightful talk. And thank you all for attending this webinar. Okay, a quick reminder is that our third webinar will be held on November 15, given by Professor Christos Masouros from University College London. So you can go to our webinar website for more information. Looking forward to seeing you all on November 15. And thank you, Professor Wong.
And I want to thank again Lena and also Anab Mishra for organizing the webinar as well. And for any of you, if you have any questions, feel free to send me an email if you have questions. Thank you very much.
Thank you. Thank you, Professor Wong. Have a great ahead. Bye-bye.
Okay, bye-bye.
Thank you, Professor Wong.
Okay, bye-bye.